In this video, we're going to show you how Gauss's law can be used to derive the formulas we previously given you. It's one of the main uses of Gauss's law, not something necessarily I expect you to do on a quiz, but it is something that I think is useful to understand in terms of how Gauss's law fits into this material. So we would like to derive the formula for the electric field of a point charge. In this case, we already know the answer is the electric field magnitude equals the electrostatic constant K times Q, the charge that is generating the field, divided by r squared, which is the distance between the point charge and the point of interest. Now, how do you use Gauss's law to get this? Well, let's start out by writing down Gauss's law. Gauss's law, if we recall, is that the electric flux, which is the electric field times the area times cosine of the angle between a vector perpendicular to the area and the electric field is equal to the enclosed charge divided by epsilon naught. So what we need to talk about is some surface in order to use this. The surface in particular that I'll consider is a sphere surrounding the charge. The center of the sphere is at the location of the charge, and the radius of the sphere will be r. Now, in this case, I'll be talking about the flux through that surface. The reason I've chosen that is that the electric field's magnitude is the same across the entire surface, and that the direction is always going to be the same relative to the area. It is always passing directly out through the area. It's never making an angle anything other than 0. Recall that the angle is between a vector coming out of the surface, so for example like this, directly perpendicular, and the electric field at this point is also going to be in that same direction. So here's an example electric field vector. Now, with a little more sophisticated arguments, we can show that indeed that the electric field has to be in that type of direction, either inward or outward. And here we're just getting the magnitude. For the sake of this class, we'll just take it as a given that it has to be inward or outward from this point charge, and the same at all distances. You can basically reason through, based on the symmetry of the problem, that the answer has to have that same symmetry. Let's look at how Gauss's law, the equation, applies to this case. If I call the charge inside capital Q, then the enclosed charge is just capital Q. There is no other charge enclosed. Epsilon naught will stay the same. The angle, as we said, was 0, and cosine of 0 is 1, so that'll disappear. And that's just then the electric field times the surface area of the sphere. And if you don't recall, the surface area of the sphere is 4 pi r squared. So if I solve for the electric field, I get the electric field is Q over 4 pi epsilon naught r squared. And also recall that epsilon naught is equal to 1 over 4 pi k times k sub e, the electrostatic constant. So in other words, k sub e is 1 over 4 pi epsilon naught. And I already have 1 over 4 pi epsilon naught showing up. So this then equals ke, this front part, q over r squared, which is the formula we started with. So now let's consider the formula for the other magnitude of an electric field that I've given you so far. This case is for the magnitude of electric field of an infinitely large plate. In this case, we found is that it was the sigma, which is simply the charge per unit area, divided by 2 epsilon naught. In order to do this, I'm going to attempt to draw a 3D version of this plate. So there's my 3D drawing of the plate. It'll continue and going on in all directions. Now what I imagine is that I'm going to draw what's commonly called a pillbox, but it's really just a cylinder. And this is going to be the surface I'm going to use for Gauss's law. And it'll extend through the plate. So that dotted line there is where this cylinder crosses the flat surface. And now this cylinder has one surface above the plate and one surface that's below the plate. And I'm going to talk about the flux through that surface. Well, why did I choose that surface? I chose this surface again because the electric field lines will go through in a reasonable direction. On the top and the bottom, the magnitude of the electric field will be the same. We know this because it's going to be in the same direction, and it doesn't matter how far away you are. And the flux then, so if, for Gauss's law, the flux is the electric field times the area times the cosine of theta. And that'll equal to the enclosed charge over epsilon naught. Now, there are three different parts that have flux. There's the top, there's the bottom, and there's the sides. On the sides, because the electric field, I'll show you some example vectors, or sample lines, will be going directly outward, meaning that it doesn't cross the sides of the cylinder at all. So the flux on the sides is 0. And then I just have the flux from the top and the flux from the bottom. So really I have three of these terms. One for the top, one for the bottom, one for the sides. The sides one is 0 because in that case the cosine of it is 90 degrees and therefore equals to 0. And then what we have is two more sides, the top and the bottom, each of which are both going outward. And the way we define this angle is it's a vector, it's the angle between the electric field and the vector that points out of the surface. Out of the surface on top is upwards, and the electric field is upwards, so the angle is 0. At the bottom, the electric field is downwards, and the angle is downwards. The vector is downwards, so the angle is 0. So what we have is two parts. We have the flux from the top plus the flux from the bottom, and that'll equal to, in this case, if I look at this for the top, the same magnitude on top and bottom times that same area, so this right here, this area I'll call A, plus the same area on the bottom, the other end cap, and both of them will be multiplied by cosine of 0, which is 1. And that'll equal to the total enclosed charge over epsilon naught. So that means that the electric field times twice the area of the top. So I'll call this area top for clarity, which is the same as the area on bottom, equals the enclosed charge over epsilon naught. Well, how much charge is in here? I told you that the surface density was the same, and that sigma was equal to the charge over the area. And this would be the area that is the area of the sheet inside of here. So in this case, the enclosed charge is equal to sigma times this area, which is the enclosed area, which is the same as the area on the top. This part of the cylinder is the same as this area as the metal sheet, the amount of area that's contained in the metal sheet. So that this area is the same as this area. If I plug this in, excuse me, is multiplied by twice the area of the top. And this will be equal to the surface charge density times the area of the top over epsilon naught. The area cancels on both sides, and I can divide by 2 to get the electric field magnitude is equal to sigma over 2 epsilon naught. And again, this 2 came from the fact that the top and the bottom both had flux through them. And this was the formula that we were hoping to derive.